In this video, we continue from our previous part where we started compiling all of our calculations, and we'll put that into the final steps of our ANOVA procedure here. And so as we move into step 3, we want to calculate the of those average deviation scores, those squared deviation scores. And so we're going to refer to this value as a mean square. And just to recall, this calculation fundamentally is the same as calculating a variance score. The only difference is the data that we actually use to put into the numerator and denominator. But once again here, these two mean square calculations have the exact same fundamental form to them. It's just that the numbers we put in are different. So I'm going to take the data that we calculated on the previous slide, slide 14, and I'm going to substitute the sum of square between and the degrees of freedom between, and I end up with a value of 12.71. That's my mean square between term. The mean square within term, I substitute the sum of squares within that was calculated on the previous slide, divided by 30, which is the degrees of freedom within, and I get 1.59. Now once I have these two variance scores, or mean square scores, I'm ready to calculate my final F statistic. This is the one obtained. So these data were generated, these numbers were generated from our actual observations from our research participants, the data we collected, and that'll give us our F obtained, which is the mean square between divided by the mean square within. So 12.71 divided by 1.59 gives me 7.99. Now what do I do with this score? I then take this value and I compare it to the critical value. Recall that the critical value was obtained from the F table, not from the actual data. We needed the sample size, we needed the number of groups, and we needed our alpha level of 0.05, sometimes expressed as a 95% for our F value, which we determined to be 2.69. So we're going to compare those two values. So before we do, just a few points to make here on the effect of the total number of participants or scores on the F obtained, or the F ratio. Recall that the degrees of freedom for the within term was an n minus k. Now if n is relatively large to the number of groups, so if there's a bigger separation, then our degrees of freedom within will be a large value. Now if the degrees of freedom within is a large value, then the mean square within will be small, because recall that the degrees of freedom within is in the denominator of our mean square within equation. And so as the denominator value gets larger and larger, our quotient, which is mean square, will get smaller and smaller and smaller. So if mean square within is small, then the final F obtained value will be large. So what this basically tells us here is that as our sample size increases, so recall in our example we had 7 participants in 5 groups. If we increase that to 10 participants in 5 groups, that would have created a smaller variance within term, because the variance calculation decreases as sample size goes up. And so as the mean square within would become smaller, the F obtained would become larger, and as the F obtained becomes larger, that would increase the chances that we would exceed the critical value. So how do we present all of our data from an ANOVA analysis? we create what's called an ANOVA table. And so this is the prescribed way of presenting those results in a concise manner. So we have the source of variation in the first column. So we have our between source of variation, we have our within source of variation, and the total, which is essentially the sum of the two. The next column, we put our sum of squares values that we had calculated. So we had 50.82 for the between, 47.37 for within, and you can just add up vertically to get the total. Likewise, the degrees of freedom. These are data that are considered to be standard in terms of reporting ANOVA. You notice here that in the next column we lose one cell. So as we go from sum of squares to degrees of freedom to the actual variance term or the mean square term, we don't put in the total because it's not used in the subsequent calculations. So we have our mean square of 12.71 for the between term, 1.59 for the within. We calculated our F statistic to be 7.99. This is the F obtained, and we end up with a p-value that's less than 0.001. So we have a far less than 1% risk of committing a type 1 error with these results. And our conclusion here is that since the F obtained exceeds the critical value, then we then reject the null hypothesis. Recall that the null hypothesis stated that there was no statistically significant differences between the 5 groups, but because we reject that, we conclude that there is a statistically significant difference in the balance scores between the different groups of athletes. So let's revisit our question here of whether standing balance performance differs between the various groups of athletes. And from a statistical perspective, we can now answer that question with a yes. The overall ANOVA results indicated there was a statistically significant difference between the 5 groups. So if we just look at the descriptive data, I'll put these up here very quickly, and we had calculated this way back on slide number 9, that the average plus minus standard deviations are the descriptive data, but now we know that there's a statistically significant difference among these 5 groups. And so this leaves us with another question. Because of the ANOVA results, we know that there's a difference, statistical difference between these groups, but not all of the groups will be statistically different from each other. And so the overall question that we're left with here is which athletes are different from each other. So which groups of athletes are different from each other. Now, because the ANOVA procedure rejected the null hypothesis, we now have to carry out more statistical testing that we call post hoc or after the fact testing, statistical testing. So we're going to cover that here on the next video on how to carry out the post hoc procedure. Now, one last point here is that if the F obtained value that we had calculated earlier was less than the F critical value, then we do not need to carry out post hoc testing. If the calculated F is less than the critical value, we would not reject the null hypothesis, and we would not be in a position to state that there's a statistically significant difference between among the 5 groups. So we would just stop our analysis at that point. But this ends this video on ANOVA, and we'll pick up on part 5 where we carry out the post hoc procedures.